on my computer and here. So this workshop is Contextual Assemblies, and I am Sanghyun, and this is a part of the Digital Futures and then the KICTT, which is the Korean Institute of the Computational Design and Technology. And my brief introduction is that I'm an architecture designer and an architecture technologist who's interested in the synthesization of human and machine cultural through computational design. I've worked with the several different AI-related research through the SciArc. I worked with Casey Rim and Damian Ivanovic and also Sumin Han before. And now I'm currently working at the Patterns work as a project designer. Before we go into the class schedule, because we have a very diverse background from all over the world, I want to have each one of you introduce yourself. Just very brief introduction so that we know that you're from here and then you have this much of a background in the architecture, or if you're not from architecture, that's okay. And if you have experience in the coding or visual coding, I want to know a little bit so that when I'm giving a lecture or the workshop about the certain types of coding part, I can gauge how much of detail I should go into. Okay, so I'm going to see everyone in the grid, and then the first one I see is Korean Yu. Can you introduce yourself about like where you're from, and then what's your background, and then what's the, let's say, your virtuosity in the coding?
Hi, so my name is Qianyue Liang. I'm Chinese, but I'm currently in Chicago for school. I go to the School of Art and Theater of Chicago, and in the first 2 years of my college, I actually majored in fine art. And so in the later 2 years of college, I started to emphasize in visual communication and the visual of human-computer interaction thing. So for softwares, I can use like Adobe softwares and Blender's After Effects. And for coding, I know HTML, CSS, and a bit of Python. Yeah, that's it.
Okay, cool, thank you. And John, you're next.
Hey, hello everyone. I'm currently in MArch2 at SciArc, so I'm okay-ish in computation design, so that's why I signed up to this to get to know about AI assembly. Thank you.
Thank you. And then the Wenjing. Did I not pronounce the name correctly? Wenjing, with the beautiful Golden Bridge background. Are you having a problem with your microphone or something? Okay, then let's go. Alejandro Garcia. Are you here, Alejandro? Okay. Then next, Moore's. Is it Moore or Moore?
Yes, Moore.
Okay, Moore. Yeah. How about you?
Hi, I'm Wenjo. I'm a student from AA Landscape Urbanism program, and my major is update data visualization, and I'm dealing with the practical strategy method, and I'm also interested about the coding, art, and the machine learning. So I want to join the tutorial and share something and learn something. Thank you.
Thank you. And Yifei, who?
Hi everyone, my name is Yifei. I work as a designer at SVM Bay Area. I don't have too much experience in coding, but I've been participating like the previous year's digital design workshop. That's it.
Okay, great. And Satarsh, I don't know if
Hello.
Yeah. Hello.
Hello. I am from India. I'm still pursuing my bachelor's. I'm okay with like coding, not coding. I'm okay with computation, and I'm very new to this like coding and stuff, and I'm looking forward to it. I have participated in your previous years Digital Futures by Kuyan Rui, and I'm looking forward to this workshop. Thank you.
Great. Hello, Carlos. Welcome.
Hi.
We're just introducing ourselves, and then the main thing that we want to know is where you're from, what's your focus, why are you taking this the workshop, and what's your knowledge in the coding or visual coding, so that I can gauge how much of the detail I should go in as a basis for the class. So if you can introduce yourself very briefly, that'll be great.
Yeah, hi, my name is Carlos. I'm from Mexico City, and I am an architectural designer, and I'm very interested in the way machine learning and artificial intelligence can improve or improve the design process and how it's going to impact architecture and design overall. And I know a little bit of Python and C# and JavaScript, but not just like beginner, maybe a little bit intermediate level. And in terms of AI, I have experimented a little bit with GANs, but not with TSNE. And I'm very curious about how it, what are the possibilities using this type of specific algorithm. It seems really cool. I've seen your videos and certain projects on your Vimeo, and it looks really cool. So very excited. Thank you.
Thank you. Okay, that's great. So more or less, I know everyone's like level where they are in the coding, and then the what your interest is, and then where you guys are coming from. Some are not from architecture, so maybe I'll keep that in mind. And then for this specific assembly, I said contextual assembly. I didn't say architectural assembly for a reason. You can actually, if you're a landscape designer, you can bring a bunch of photos of a landscape design, or you can put different types of vegetations, and then trying to see how or what this TSNE or the algorithm will give you in terms of assemblage based on the similarity and the dissimilarity from the one to another. And if you don't want to do that, you can also have a bunch of a cat photo and dog photo, and then have them assembled, and then we can make something cool from that as well. So in terms of images, as I demonstrated in the email before, you can use whatever image that you want, but then you need to have some consistency throughout. You cannot have, like, let's say, architectural facade with the dog photo, because that's way too different, and then it will still work, but then it will not make a very consistent data set. So what I'm going to cover is a technical also, but also at the same time a little bit theoretical, because when you're designing your data set, that's actually the most crucial point of your design process for the machine learning, when you're using machine learning tool as a design tool, because it depends on what kind of a data set you're going to have in your tool. Your result a little bit predetermined by your data set. just like we start with a certain precedent when we design the architecture, it will bring certain nature of that project into your architecture. It's basically the same or similar process. Okay, so if you have your own data set, that's great. I would love to see what kind of things can happen, especially people from the different field. I think that would be amazing to see what kind of thinking that you're bringing into this process. I would love to see. But if you don't, and then if you're just from architecture, I provided my own data set to the email, everyone in the list. So feel free to use that as a reference. But if you have your own data set and then follow through what I'm doing while I'm doing the workshop, that would be most helpful for you to gain the knowledge and to understand the process and why certain things are important, why certain things are done this way. So please keep in mind that if you're following this, that's going to be most beneficial for you. So for today, I'm going to cover a little bit of a theory behind the TSNE. By no means I'm a computational scientist or a statistician. So I'm going to be wrong about many things, but I want to cover basically generally my understanding of how this tool works, and then based on some publications that I've read before, I can give you a little bit of a more insight to how TSNE works as a tool than people who have never used it. Okay, and then after that, we're going to cover how to collect and process images for machine learning using processing sketch, which was also attached in the email. And then we're going to use both Photoshop and processing to handle the large size of a data set. And then also, after that, we're going to use Google Colab. Google Colab is a great tool for someone who doesn't have a supercomputer in their house, but still want to train their own data set or run a big data set through very powerful graphics card. Google Colab is free unless you want to do Pro, and you can borrow their graphics card or CPU for free for a certain amount of time. And then this is a very popular tool right now. And then this is one of the reasons why machine learning tool is so very popular among the designers and then architects and 3D artists and everyone, and make it very accessible. And based on what we have learned today about the TSNE and then all the data, how the data works, we are going to run some examples of the different types of a TSNE, how it's run on the Google Colab at the end. And if we have time left, I'm going to cover how the Google Colab works in the form that we're going to use, which is called the TSNE Grid Maker. Okay, so that's the schedule for today, but I also want to give you a brief idea of how the rest of the days will go by for the tomorrow and then the Wednesday. So for tomorrow, we're going to get a little bit serious about the coding, and then we're gonna use Python to write your own algorithm from the scratch for the TSNE. It's not that complicated. If you go into a detail, it gets complicated, but then I'm going to make sure that you understand every line when we're covering this. So don't worry about it. If you don't have a prior knowledge about the Python too much, let's say if you know just the basics of a Python or C# or any kind of a computer language, you can definitely follow it. Even if you don't have it, I'm going to cover very basics like syntaxes and then how the algorithm works or the Python or any computer language works. Briefly, so I can cover that. And if you still have a hard time after I cover this, you can always come back to me at the end of the class, ask questions. The reason why I set the time from 8:30 to 12:30 is that for me to help you troubleshoot certain things as well. So don't be afraid to ask a question. You can interrupt me anytime when you have question. I will help you. So don't worry about it. And once we finish writing the TSNE algorithm, we're going to put that in the Google Colab. It's a little bit of a process. It's different from using, let's say, you're using someone else's Google Colab. If you're implementing your own code into the Google Colab, there are certain steps that you need to go by. So I want to cover that and make sure that everybody has a running Google Colab page. And then we're gonna try some variations of the code that we wrote here by changing some of the variables and see what's impacting the result from the variations of the code. So that way, you probably have a better, we'll probably have a better understanding of how the code works that you wrote or I help you write, and we can play with it a little bit. If you have your own data set, it'll be very fun to play with. If you have a bunch of cat photos, if you have a bunch of vegetation photos, or your hometown photo, or whatever photos that you have, like it could be your friend's face. You can see how one friend of yours face is relating to another friends of yours face in terms of how machines see it. I think that's interesting. So that's going to be pretty fun. So if you don't have your own data set, I would really recommend just go through your phone and then get some photos that you can find on your phone so that you can actually play with this, okay? And then we're going to introduce the Houdini. For those of you who don't have experience in Houdini, it's okay. I'm going to cover it from the really basic. This is not going to be the code that we're going to use for our projects, but then this is more of an exercise at the end. And then tomorrow, not tomorrow, but then the day after, we're going to really dive into the Houdini for the more of a project-specific purposes. And we're not only going to use Houdini, but then also using Blender to show different kind of possibilities that's available for these two the processes. And then once we create these geometries, we're gonna put this into V-Ray. I know a little bit of V-Ray, but probably not as good as the Quenu, but I'll try my best to cover it. And then yeah, that's basically mostly it for the workshop. If I have a time, I'll try to cover the Rhino penalization tool. There's a Rhino add-on that you can install on your Rhino, and then for whatever geometry that you have, you can actually attach your facade element into that geometry. So that's something that I'm hoping to cover. Let's see how much time we have at the end of the day. And then after that, of course, I'm going to do some troubleshooting for you guys. I'm sure many of you would have some issues on the way. I might have any issues on the way, and then I'll have a general Q&A, and then we'll close down, okay? So that's the schedule for the 3 days. Is there any question about the schedule? Okay, so if we don't have a question, I'm going to cover just the general content of what we're going to do for this workshop. So this was actually a part of my thesis research a year ago. And I started with this question: how does machine sees the city? For us, it's very obvious what part of the city is at this part of the city, and then how does this building relates to this building, or how you feel when you arrive at downtown LA, or how you feel when you arrive at, like, I don't know, Hollywood or West Hollywood. It feels very different from one city to another city. Seoul is very different from LA. LA is very different from New York. But then, can machine really identify it? Can they really see it? I was really curious about that, and then I was trying to compare how one image to another image differs to the machine's eyes. And then relating back to how we see the city. Can we really see it apart when there's only a segmentation of let's say, facade elements that's shown in certain photo? Can we really identify that? Now we have all this like captcha, like when so it will ask you, are you human? And then if you check the box, it will show you example of, let's say, bicycle, and then you have to pick out what's the bicycle, right? So I think that's actually quite interesting, because they're not only using that as a method to identify you as a human, but then at the same time, they're using your brain, as a machine, as a build to build a data set for the machine learning and other AI purposes. So the images that you identified on this image capture will be used for someone else's research or someone's benefit. I think that's super interesting, and that's where my question started. So now, when you go to Google and then type Los Angeles architecture, first thing show up is Frank Gehry. Second thing, the Broad Museum. Third, I'm not sure where it is. And but then overall tendency is that there are many repetition of the images, a lot of Frank Gehry, a lot of the Broad, some mocha here. So it's, for me, it's a little bit weird, because when you actually go to downtown LA, there are a bunch of different types of architecture. The architecture from like 20s, 30s, even before. And when you go to the financial district, then you will see more of a newer building with the curtain wall system. There are so many variations in the city, and if you're just Googling it, you will miss it. Like, actually, you would think that Frank Gehry building and then the Skip Video building, there may be the most prominent building of the downtown Los Angeles, but then that's not everything. Instagram has the similar tendency. There is a Mocha, there's the Frank Gehry building, there's a Morphosis building, Kopimilov building, the Broad, and then the famous Eastern Tower. And the Flickr is quite the same. A lot of a Frank Gehry building, and then there's the hotel, and there are some inside of the Broad Museum. There's a financial district, but then it doesn't really represent the full variety or full diversity of the downtown LA. So I actually wanted to represent the downtown LA as a whole, and how the machine sees the relationship between one to another, and then you use those images as my inspiration for the facade assembly. So how does the machine truly see the human culture? I think that was the crucial question for me. Through the this is the diagram that I took from the Bruno Latour's "We Have Never Been Modern." What Bruno Latour is saying is that there is a certain division of non-human to human agents through the process of modernization. But then, actually, a lot of things are in this hybrid network that's non-human is not completely separate from the human, nor human is completely separate from the non-human agents. So we're still on the work of a translation. If this was a work of a purification between the nature to the human, it's a separation. And now we're actually in the work of a translation, how we combine the human agents to the non-human agents. And I wanted to see this kind of let's say, philosophy in my workflow, where all these elements are built or result of the Anthropocene. Everything that you see as an image here is a result of a human construction, but then non-human agent, in this case the AI or machine learning agent, is working to combine or reconfigure these types of conditions, and then make this giant object that is basically a conglomeration of an aesthetics of the downtown LA. Let me go to this page. So these data sets, I actually went to downtown LA and then took the photos myself. So in this particular process, my agency is already in. It's the evidence of a kind of human labor, and also my personal taste in the architecture. I thought that some are worthy to be included in the data set, or maybe the parking spot that I found in the downtown LA was closer to this building or that building. So this building is included in the data set, or that those buildings are, or other buildings are not included in the data set. But then that's also part of the human culture and how we think or how we operate. And these are more, these were cooked, let's say, in the form that's more digestible for the machine learning agent. You can see that I'm being very precise and then the consistent throughout the data set, how I cut these photos. I basically perspective matched to be more orthographic images rather than perspectival image, so that it is easier for a machine to digest it. At the same time, there is always the central kind of object within the frame set, within a frame. So this is from the same building, but it has a different form of windows. Sometimes it has articulations. Sometimes it's completely different building, but in terms of overall building scale is pretty much the same. You see, this is a 3 windows. That's a 3. I mean, this is 3 stories, and then this is also 3 stories. You can see that I'm being quite consistent. And this is my attempt to work on the translation between the human understanding to the machine understanding. And as a result, when I use the TSNE, this is a machine's understanding of how one facade element relates to another facade element. You can find almost this around this area to be more, let's say, contemporary method of building, curtain walls, and this is actually parking structure, different types of the curtain wall, and then this is a metal, what is it? Metal panelized the facade. Whereas on this side, these are more of a masonry or veneer, masonry veneer construction. All these facades were less glass or metal, but more stone or brick. So more of a ceramic kind of a condition here. And then when you come here, these are something else that's machine was confused if this was a facade or if this was the curtain wall or not, because there is a mixed use of a stone and then the window. There is a so it's actually quite interesting how you are trying to read what the machine give you as a result, and you will experience the very similar thing when you let's say input when your input is, let's say, cat, like different types of cats, then you can kind of tell how this algorithm thinks this cat is more closer to this cat. Maybe this cat is a fat cat, and this is a skinny cat, and then this is maybe black cat, and this is brown cat, and this is like a white cat. It will show very consistent, let's say, tendency in terms of how this algorithm wants to array things in and out. So that's, I think, as an tool to communicate between the machine to human is very very interesting. And whenever you run the code, what's interesting about the TSNE is that there is a, let me see, I can draw here. So you see this as a 2-dimensional grid. Let me pick a different color. This is not a good color. Yeah, you see this as a 2-dimensional condition, but then what happened in the TSNE is that it's actually more of a 3-dimensional cloud. it's like three-dimensional cloud. So it actually has a depth in it. And then this is only representation of this the three-dimensional cloud into a gridded condition that I defined. And then it is trying to retrofit the three-dimensional cloud condition into the two-dimensional data. So that's because of it's always going through this representation. Whenever you run your via TSNE, even if your variables are exactly the same, it will spit out different results every time. But the relationship between the conglomeration to another conglomeration will be always very similar. You can see that this is always neighboring with this one. You can see that this is always neighboring with this one, and then this blue tone of the curtain wall is always all together. And then you can see that all of this is always together. All of this is always all together. So you find the tendency the same, but then the result is not randomized, but then it's showing certain tendency, but not like an exact pattern. Okay, so that's the, I think, unique thing about the TSNE. Okay, so after that, this we might not cover, but then considering everyone's the virtuosity in the coding, I don't think that we're going to cover this. But then just to give you a general idea how I work with it, you see all this image assembly that the TSNE gave me. I basically harvested the average color of each grid, and then turned it into an RGB value here, so that I was trying to average whatever the aesthetic element within this grid, and then I tried to generalize this through the map condition. I had 32 point clouds that was collected and then was in the list, and then based on that the list condition there is like 32, and then whenever this is closest to certain color, I try to put 1/32 into this grid condition to simplify my design. And on this one, I was trying the same, or I was expecting for the same result, but then using different strategy. Here, I was searching for certain features right here in that image directly. I didn't do the average RGB value. I used just exactly this image, and then try to simplify my facade design based on this 32 again, and then what this algorithm thought that the most closest thing to whatever this image was that this blue element, and then whenever there is a little bit of a yellow tone, the machine chose this orange tone. So this is something that we can cover if we have time later on, but then this is not the priority. It's just to explain what are the possibilities and what can be done, or what I did in terms of my own project. You will see I divided the downtown LA as an east and west based on my site condition. And then based on the east and west, they have a very different color scheme, very different aesthetics, because most of the east side of the LA is a old construction. The Broad Street is there, and then the Broad Street is the old street there, from back in let's say like a gold rush. And then whatever on the west is a new construction. Disney Concert Hall is there, Mocha is there, the Broad is there, Financial District is there, everything new is over there. So I wanted to see the contrast between the one part of the city to another city, and if the machine can understand it. Go to next. And this is a process that we're going to use with the Houdini based on the 2D image. We want to create this three-dimensional the tessellated the elements so that we can use this as a more of a 3D representation rather than 2D representation. This brings a very interesting issue here because you're representing a building in the form of a photo, and then you're representing that photo into the digital environment where you use Houdini or Blender or whatever tessellation tool that you're using. And once it's tessellated, I'm using the texture map to apply on that tessellated surface. So it's actually a little bit far away from the original state of the reality, but then it's a more of a digital recreation or digital representation of how one reality is transformed from a version to a representation that's based on your decisions on the how detailed it's going to be. Do you want to do voxel? Do you want to do curvature? Do you want to do this color or that color? It's up for you to redesign, right? So that's a part of the process. And this was the final product for my research. Some of them are manual, some of them are automated, but then mostly to generate this tessellated facade based on the TSNE, the compositor. I made all these decisions, and then trying to best represent the around the area of this specific site condition. So you can see this. Let's say this is their Broad Street, which is the most, let's say, historical part of the downtown LA, and a lot of the facade condition here is based on the masonry or the brick masonry or the granite masonry, or even if it's a veneer condition. On this side, the harvested images were heavily based on that more of a tactile material, and on the other hand, this side is towards the west, which is a new part of the town, and then this represent, even for the masonry, it's more of a contemporary expression of the masonry, and this is a curtain wall. This is actually a Ritz-Carlton building, and you will see a bunch of other forms of new emerging forms of architecture. Not necessarily the best condition, but then you see one of those like buildings where first floor is the retail or commercial, and then the second, third, fourth, or fifth they're residential. These are those buildings, and then of course the parking structure is a very much of a essential part of the downtown aesthetic. So I included that. So
it looks really cool.
Thank you. Yeah, so you probably have noticed by now, it is the we're relying a lot of parts on the AI or the machine learning tool or any sort of coding, but then there are a lot of decisions as you as a designer to make. So it is important that you guys think this through in the beginning of the process so that you can control a lot of variables towards the end. For instance, if I didn't cut these brick facades to be that particular proportion, this wouldn't have worked, right? I had to think about the scale. I had to think about how this will be compared to another, let's say, sets of the panels. So these are some considerations that you need to make when you're working with the machine learning tool. It doesn't only apply for TSNE, but then it also applies for the like any kind of a GAN work. You need to always have a consistency throughout your data set. Otherwise, we usually call it contamination in your data set. Once you have a, let's say, more than like 5%, I'm not sure if that number is correct, but then just to make an argument, let's say if you have a more than 5% of a contaminated data set, your training result will completely ruined or will not be so good. So that's something to be mindful about. And yeah, these are all the collections of images that I have went through, and then these are the assembled parts of the downtown LA. And this is West, and this is all together. And you've already seen this, but the thing that's running on the background here is the Stallion. Stallion is something that's not going to cover today. That I'm going to cover today. But if you have any questions, or if you want to have access to the code, I can help you guys with that. It's very popular right now. Everyone's using it, so I felt like maybe it's not worth the workshop content. But I can definitely help you guys train your own data set if that's something that you're interested. You see like how one facade transformed to another facade in different types of different parts of downtown LA. Okay. Yeah. And this is not something that I'm going to cover. And if you guys want, I can cover the Unreal instead of a V-Ray as a data visualization tool. I'm okay with both. So if you particularly want to learn this kind of a point cloud aesthetic, I can help you guys with this too. So just let me know, okay? So that's about it for the my own projects demonstration, or what we're going to cover. Now I'm going to cover the content for the Photoshop processing workflow to prepare your data set. Before we go into this, do you guys need a break, or are you guys okay? Keep going. Any votes?
Sometimes keep going.
Okay, yeah, let's go. So how to prepare data sets for AI? AI, especially for the let's say GAN specific tools, you really want to work in this types of image sizes, because these are the multiplication of the two. You know how computer always works in like 1010, and whatever the x number of the complexity that you're going to introduce, this is always going to be that number, like the multiplication of a 128, 20, 256, or 512. If you ever bought your computer, you probably noticed that your RAMs are like 8, 16, like 32, 64, right? So there is a reason to it. And then the image is is the same. You always want to have this multiplication number. And segmentation. Segmentation is another part of the story, because this is for both human and machine. When you have, let's say, an image of a person, a portrait. There's a very pretty guy here, and why do we segment? Segmentation means, oh, you're going to divide this into this grid condition, and then you're going to, if this image as a whole is called 1, You want to have 1/1, 112, 13, 14, and so on. This is because you want to have background information and then foreground information. And then without segmentation, it's hard for AI to understand what is the foreground or what's the, let's say, what's the figure and then what's the background. And if I elaborate a little bit more on the figure and ground condition, you're all from the architecture or the in the vicinity field, so you probably already know what I mean, but then I just want to clarify this. So this is a figure, this is background, and you want to give as much as information as, about the edge condition between the, so if I, let's say, zoom in this, this is edge condition, right? This is background, this is foreground. And from this image segmentation, the machine learning tools, mostly machine learning tools, can learn about how are the edge conditions between your subject to the background information. At the same time, if you have to produce all these figure images, maybe this one has a long hair. Maybe this one doesn't have an arm. So you have to make all this like photo with the different, let's say, subject for each photo. But then by using this method, especially if you're interested in the elements, not the whole, you can multiply your image resources by a lot. Let's say this is 4x4 grid condition. So with one image, you make 16, right? So that means your work is reduced by 16th of a fraction, right? So I'm okay with reducing my workload. So that's another reason for it. And we're going to use the processing to automate the segmentation process. So from now on, we're going to do a little bit of Java. So let me bring up the script right here. I'm going to explain this first a little bit, and then I'm going to cover writing this from the Scratch. So this is called the image splice overlap. This is to divide images into divide an image into many different many segmentation of images. P image in IMG is just that you are importing whatever the asset you have in the processing. This is a PZChem import, and you can turn on the PZChem in your the processing. It's one of the add-on. And the int is called the integer. Integer is an let's say 0, 1, 2, 3, 4. This is integer. And the string, this is integer, and then the string right here. String is a tag. Like you have an like clothes, and then it always comes with a tag, and then it describes the name of the clothes, price of the clothes, right? So it's exactly the same. So whatever object that you created in this like coding environment, you're putting a tag with the string. So because of that, we have that as a namespace. Namespace means the name of that object, right? So pretty easy. And then another string, we're defining a string which is called the outer, which is short for the directory of your output. You will have also input, but then that's not yet defined over here. And let me clear out the thing. And here, float is a little bit different from the integer. Integer is always a set value, like int equals 0. You see it here, like int count equals 0. That means that it's going to be 0. Float is something that you can change in between, let's say in range. If you have like a 0 to 10, like for instance, in a grasshopper, you have a slider, right? Going up and down. That's basically your float. But you know, it also can be redefined in your code. That's a bit different. But here in the void setup, you remember the high school math when you had like a y x plus 1, and then you put 1 x equal 1, then your y is 2. This is called what? This is called function. And then you're basically setting up a function through this parentheses. Whatever that's in that parentheses, this is a part of your equation. Okay. So it looks a little bit more complicated equation than y equal x plus 1, but then basic concept is quite the same. And right here, we're defining a step x and step y. We're when you have a, let's say, image that is this big, we're defining how many steps that it's going to cut, how many steps it's going to cut on the x and y axis. And the namespace is again just like defining a name. You already defined a string namespace, but you didn't give it any value. So this is now empty. So imagine you have a bucket that's named the namespace, but then there's a nothing here yet. But then when you call cat is coming in. So now your bucket is a cat. See, so it's that's kind of a concept for the string. When you call out whenever with this the quotation mark, let's say you define one more time on the next line or outside of this function, not cat, but then like dog, then you're suddenly kicking out the cat that was in the basket, and then put the dog in that basket. So you replace whatever that was defined before. But I'm going to delete this, and the image equal load image. Whatever this the highlighted as a blue is an embedded function within the within your processing. Load image is a known function for that, or included function in the physicam. So you load the image that is called this particular name from a directory that is already set up in your image splice overlap processing folder. This is the processing folder, and usually your source image goes into this data. We'll cover this more in detail later on, but then I just want to demonstrate this before we go into the actually manual coding. Okay, and this is how processing is cutting the image. Now this function from void draw to the end, all this yellow area, is the code that tells the machine to cut this image into this X, Y, and Z. I guess I missed the explanation, but then the floor is to just put the image in, on the floor. Literally, you're putting an image on your like a living room floor. It's basically the same. So it will have a space in certain digital space so that you can change other things around. Human oftentimes don't need the reference point, but then computer always needs the reference point, right? There's always, in whatever CAD software, there's always origin, and then there's like 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and then you tell the computer, you start from the 3, and then you draw a rectangle that is the size of a 2, then this is your rectangle. Computer cannot just draw something without reference point. So that's why we're flowing. Here, you defined another variable, which is the count x, and then the count y, which is defining your image size for the x and y axis. And then this is for loop. For those of you who never coded in your life, you probably remember high school or middle school class where you have this kind of a diagram. You go here and then you do this, and then if this is yes, then you go here. If this is no, if you go here, and if this is yes, you go here. And sometimes you have to go back to the original point. So this is the origin, and then this is like a certain node condition, and then the node condition will return to your origin point. And then this process of returning the value whenever the condition is satisfied, we call it for loop. There's a for loop, while loop, and there are many other loops, but then for loop is the most basic and the most often used loop that you can think of. So this for loop is identifying this new variable I. It's basically same as the x, y, z. Instead of x, y, z, we're just using I, j, sometimes I, j, k. So you don't have to use I, j, k, but then that's more of a convention instead of using x, y, z. X, y, z is actually quite particular for the Cartesian coordinates. So to avoid the confusion, we use I, j, k. And I means like the first variable, j means the second variable, and then k, if you need the third dimension, you use k to define the third dimension. In this case, you see one for loop and then another for loop, right? But when you think about your graph, for instance, this is your x, this is your y. This is something that you never think about as a human being, but then defining a two-dimensional element requires a two for loop. One, you have to, so let's say x or a point is equal to 1, 2, right? This is point, right? To define this, human brain work in a little bit of a parallel way. So here's 1, here's 2, so this is this is the point P. But then machine, they process 1 by 1, so they define the first one first. So when you first start maths, when you're in your elementary school, we probably did this before. So when x equal 1, then this is all the possibilities on the x equal 1, and y equals 2. This is all the possibilities within the y equal this is y equal 2, right? And and then computer is trying to find the intersection between the x equal 1, y equal 2. That's right here. Does that make sense? Okay. So to proceed from there, this mark here, the when I is smaller than count tx, which is the maximum distance of your image. Let's say your image is like this. This is count y, right? Then you're just trying to figure out what is the maximum I you can reach until you meet the point of the limit, right? So you're on the first iteration of this for loop, your I will be 0, right? I is 0, but then I is still smaller than CNTX, right? So it will add, so it has a 2 plus mark, but then don't get fooled. It's just a convention for the +1. So from 0, you have now reached to the 0.1. Just one, and then the one in the another iteration of a run, you keep increase the interval until you reach the count x, which is a predefined over here based on your image sizes, right? And then the what's happening here then? This is indented by a tap. When you press tap in this environment, you will have an indentation. This is not just for some aesthetic or fun. It is very serious, and you have to align it perfectly. Otherwise, this will not run. Okay. So once you define the x-axis, or whenever you're running the I on one iteration, you're running the j as well. So this is 0, and it's going to check from the 0, 0, and this is like a ij, and then the next one you're going to run 0, 1, right? And then 0, 2, 0, 3, and so on. And then on the next batch, you're going to run 1, 0, and then 1, 1, right? So it will try to fill the matrix of x and y. I mean, I and j. So ij, and then every possible things like 0, like 1, 2, 3, 4, 5, and 0, 1, 2, 3, 4, 5, and then it depends on how big your image size is, and then depends on how many steps that you have defined before. This is going to create different types of a matrix. Okay, and here now you're bringing the int x, which is another variable. This is a step xy. Whenever you see this, you can always go back to it, and then you already defined here your aimed image size. So if you, let's say, have a 1024 by 1024 image, 128 by 128, then that's how many? 8 images. So you will have 8 images. We know it by our calculation, but to really manifest the calculation in the coding world, you have to do all this process. So this is basically defining the how many cuts it's going to make, and then the what sizes are these the cuts, and then the once each frame is cut, you're going to save that as a frame, and then the it will so let's say you have this image right here, 0.png, then you're going to like this kind of a cut from that image. You see what I mean? So but then this is actually not a great example, because you have this image, and ideally you either want to cut in this way, or if you want to have like some sort of rectangular image, you want to cut it like this way, so that your data set will maintain more consistent throughout your whole set, right? So this is something to think about when you design your own data set. Okay, and now I'm going to I'm going to close this, and then I'm going to start new processing. So here, this is the empty sketch file, and I'm going to write from the scratch, okay? So before we do anything, you always want to import your library first. This is same for any sort of a coding practices. So sometimes just figuring out what you need for the code is very, very important. For this one, because this is a quite simple tool, we don't need anything more than the PZCam. And then to import the PZCam, you can type p image. And then we're going to call it image. Call out the image part of the PZCam. And before we do this, like, do you have any question? Does everything make sense so far? Or I know that some of you don't have a background in the coding, so I'm just making sure that you're following. Okay, but before we go deeper, I just realized that there are two different languages that you can use for the processing. One is Java, one is Python. For me, most of the time I use Java for the processing. So just you need to make sure that you're running Java, not the Python. Java and Python are very different language, so make sure to change this. And we now are going to define the integer. Integer. What do you need when you think about dividing your image? You want whole image, and our goal is to segment it. First thing that you can reasonably think is that you want overall sizes, and you want to know your target size, right? So these two things are the most important things that you can define. But then in the case of the whole image, size of the whole image, you can basically harvest it from the original image, or the image that you're going to use. But then this particular area where you're defining the sizes of your image, the goal image to goal size image, you need to define for your own, right? So first thing is going to be defining the x dimension and y dimension of your targeted size, which is I'm calling a short for the dimension dim. This is going to be for the throughout dim x equal. For my case, I'm going to just use a 1 to 8. And we also need to define the y. Okay, question? Oh, you're muted. You're muted. You're muted.
Oh, sorry.
Yeah.
I mean, could you please zoom in a bit, because the window is very small for me to read.
What was that?
Zoom in a bit.
Zoom in.
Because,
Zoom in.
yeah.
Okay, let me see. I did this before. Was it in preference? Font size 36. Also font size 24. Is this good? Better?
Yeah, it's good.
Okay, great.
Another quick question.
Yeah.
Will you upload this the recording tonight?
Yeah, I'm going to share it. Yeah.
Okay.
The Zoom recording link.
And okay, cool.
Yeah.
Thanks. And for the 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 library that you just mentioned, the
Yeah.
PZCam.
Yeah.
Like I know you typed it. Like, shall we import the library from
Yes.
like this? Like,
Yeah.
I'm just wondering.
Here on the sketch, import library, add library, and depends on what version you have. PZCam is sometimes embedded in your processing, but then just to make sure you can type PZCam, like you see, this is PZCam by Jonathan Feinberg. You
Right.
can install this on your processing, then you don't have to worry about after that. But then even if it is installed, you always have to call it out with the P image.
Oh, so I have to do that first, and then I type every single time, like
Yes.
to call it out. Okay, thanks.
Yes. It's like calling a name, right? If I call John, like John will react, right? Because that's his name.
Thanks.
Yeah. Okay. Okay, I will keep going then. Any more question? No. Okay, so now we defined our goal dimension for the image cutting, and there are a few more things that we need to define because we need to know how many, let's say, if it's a 124 by 124, we know that if it's a 128 by 128, it's going to be 8 images, but then the computer doesn't know, and then let's say this number is not 124, it's like this like big number, then we cannot like calculate. So we cannot know how many steps that it requires to go through this cutting process. So what we're going to do is that if we don't know it, we're going to just give it give the step an empty value. Step x 0. This putting a semicolon is a convention in the Java to notify your computer that, oh, I'm done, you know, this line I'm done, and yeah, and enter, then you are starting with the new line. Actually, if you just no, never mind, let's not overcomplicate. Yeah. So int step y equal and then semicolon. So now we know that we're going to cut it with this, and then we don't know how many steps it requires, but then the steps there as an empty bucket, we can fill it out later. And then now also we need to define the name of the file. But then we don't know the name yet. So we're just going to give an empty bucket, right? String, for the string, you have to capitalize the letter S for the string. So make sure that you use the capitalize. So if you, easy thing to notice is that if you are using wrong syntax, it will yell at you. The class string does not exist on the bottom, right? So now when you put the S as a capital letter, it will you'll be happy. Right? And, we also need to know where we're going to spit this out. So that's going to be our out direction directory, out directory. And in terms of how many counts, we don't know. We can do CNT or count, but for the efficiency, I'm going to use CNT instead of a count. And we're also going to define the float. And then this factor too is defines like how much it overlaps between the one cut of the cell to another cell. So if you have, let's say, 128, you're going to overlap 2 pixels between the one image cut to another image. So let's say you.
Korean.
What was that, Angelo? Did you say something, Angelo?
No, mi sembra rotto, però. Fatto cazzo. Devo cambiare vita per forza.
Okay, I'm assuming that's not about the workshop. Angelo, you have question? Okay. Okay, I'll keep going. So if you can have it as a 0, that's fine. But for me, I'm just going to keep it 2. And now we define all the necessary variables in this section. So we can now start writing a function. And remember, to write the function, it's same in, let's say, C#. C# and Java is a little bit similar. So if you're quite well versed in the C#, you can probably follow the Java right away. So void is still always like a start syntax for the function. And you call setup. Setup is basically your baseline. Like when you start a game, when you start a new game, you need to make a character, right? Like that's like a base. So this setup is to set you up, like to take on an adventure. So you need the setup no matter what in this like Java setting. So you start with this, and it's a good practice to always start and finish with your parentheses. It's on the setup, you can actually have some sort of a name here, like it's like this, but then this is not necessary, so I'm just going to skip that. But if you're dealing with very complex the coding environment that's dealing with multiple node conditions, you probably want to name your the function. So this is the location that you put it. So now we have open empty function. So inside of this empty function, you want to fill it up. Make sure that you always finish with the bigger parentheses, and then put all your content inside of your this parentheses. And kindly, the processing sketch app will give you spacing, the tab space automatically for the indentation. As I said, indentation is a way that a lot of a computer language identifies the hierarchy. So if this is let's say this is a king, then you would have like a bishop, and then you would have like a knight, you would have like a pawn. So it's like this. If you're bringing the if you bring the chess as an example of a hierarchy. We're defining the sizes. We already kind of have this like sizes defined here. So you can either use dim x and dim y, or you can just write down right here. Okay, so this is the and I didn't mention this before, but then this the slash, if you put it twice, this acts as a comment. If you want to come back to it and then check again, you can have this as a commentary. So after this is a named image size. Just to remind myself, when I come back to it like 2 years later, I still know what's going on here, right? Whatever that's written after the this 2 slash, it would not be included as a part of your the code. Okay. And you defined the step x as an integer before, so you don't have to define your int step x like this. You can just call the step x as an as a thing, as an object inside of your code. Step x equals floor. Floor is literally like flooring your image on your XY space. So step x, we want to know how many steps it requires to fill that the sizes, right? Size of the image based on the target size. So this is going to be float dim x and the vector. Actually, I come to think of it, this I mentioned it, I think, incorrectly. So this is a 128, and then I told you as if this is going to be 1 to 6, but actually it's not 1 to 6. If it's a 1 to 8, the next image that you're going to cut will cut in overlap. Okay, 1 to 8. So in reality, you would have 64, 64, 64. So you're creating new content every 64 pixels. And the purpose of this, not for this workshop, but then usually the reason why we are using this is that to create some sort of a seamless transition from one image to another image. When you use Photoshop, you know what you probably know what I'm talking about. You can identify this as a smooth transition, more of like a transition area between the content A to content B. So that's why we're using this kind of a convention. But then if you don't want overlap, you actually don't have to use this function, and you can just call your factor 1, because when you divide something by 1, it's still the same thing, right? So this is for the overlap. Before I confuse more people, let's put this here. This is deciding the overlap amount, and then by dividing the origin. Right. So we're good now. Always end with the semicolon. So y equals to we're just defining the size of the image. Okay. Namespace equal. Now this is the name of your photo. You should put it in this like a data folder. Let's actually save this right now. If you save this as, I'm going to save it. Processing. Where's the processing? Well, it doesn't matter for now. I'm just going to save it on my desktop. And this. So you'll see this kind of a folder here, and then the if you, I don't know if you guys can see it very well, but this is the with the PDE extension. This is for the processing, and once you have that, just like I had before, right here, you would want to have this data folder. Data folder is a preset for any sort of data storage in your processing specific. So if you put an image inside of this data folder, I'm just going to bring one from here. What would be good example? Okay, let's put this amazing architecture here, and I'm just 40 just for the simplicity, and we're good. And now we know the name would be the 40. Um, and when we're calling out that image, we can say 40.png, and this will load this image 40 into your the coding space. Okay, and we had predefined outer, which is the out direction of the directory of the this image set. But that's an empty string right now, so we're going to define that in this function. In my case, actually, it's going to be in this desktop. So you see that whenever you put your cursor on and click it on your window explorer, you can copy your directory of your file, right? You can make another folder here out there, and you can copy this into the your space here. But then the one thing that you need to make sure in the processing is that the backslash means something in processing. So you cannot use backslash. So what you have to do is press Control F and then find all the backslashes and then change it to the forward slashes. And how to do that? You just type it like this and then click the replace all. Then you have replaced all of your errors, and then now you can finish your sentence right here. So that you now define your out direction and make sure to close it out with the slash at the end, and then also put the semicolon at the end, right? I know that this could be super boring or super overwhelming, depends on where you starting from, but then this is actually pretty good exercise to get to tomorrow, because tomorrow we're going to do a little bit more of a hardcore Python coding. Java, exercising this like a very simple task in Java is a good exercise to get ready for tomorrow. Okay, so this is like a pre-workout. And now we have defined everything that's necessary to write our cutting function. So this is all defined now. You now have a aim size, and you know the steps, and you know your name of your file. You load your images, and you know where it's gonna spit out. So we're good to go. So again, to start a new function, you need to start with the draw, the void, and then usually for the processing sketch, you say your function draw. Draw, as you can imagine from the name of the app, processing sketch. So that's why it's you know, doing a draw convention. And same thing, you start and then finish your parentheses first, and then you create your content inside of the function. Okay, and as I covered before, we're going to define the count x and count y, but then instead of using the full count, we're going to use a CNT as a count, and in the CNT x and then CNT y. Okay, and then we cannot just leave it empty. We have to define it. Now we know the dimensions of the images, or the steps of the images. So now we're harvesting the image sizes from this 40.png. Okay, and then this image dot width This is a function. How it works is that you remember in the beginning of the code, you identify img as an library, right? This is for the PCCam. And this img is a PCCam specific function, and then you're borrowing their tool. So we're basically crediting the PCCam, right? img dot, and then after the dot, you can use whatever the function that library includes in their set. And then the image dot width is one of the functions that you can use in the basic PCCam. Image dot width basically measures the image width, which is this dimension. You measure this dimension, and then we predefine the steps here, right? So what it's going to do is that dividing this image width by how many steps that you're going to need. Okay. So right here, I'm going back to X and make sure to close it twice because there are two parentheses and semicolon, and same thing for the Y. Just this is going to be Y, and then instead of the width, it's going to be height. This. So we now understand how big the image is, and then how many steps there are going to be for the height and then the floor. But then we don't know the specifics of how this is going to operate. So now we're going to define that through the for loops. So here, for int I equal 0, because I is not defined anywhere else before, so we have to define it. I is smaller than the count x, we increase the I value. For the another dimension, j equals 0, and then j is smaller than count y. So I is corresponding to x, and then j is corresponding to y. And this is going to be j plus plus, and then for the content, we are going to use this opening and then closing of another parenthesis. And inside of this for loop, that's where we're going to put all the content, okay? We're going to do the int x is equal to the I multiplied by step x. And the int y equal j multiplied by step y. You see what I'm doing here? So we have this images, and we define the steps, but then we know how step is working as a function, but then we didn't know the exact value of a step. Through this process, we are figuring out how many steps do you need for the x and y exactly for this specific image width and height. Okay, so this is the process. So how many how many steps that you're going to have, this is the number of the image that you're going to create as a grid condition. So if this is a 3 by 3, your I value is a 3, your j value is a 3. So overall, you're going to create 9 images, and then the naming convention for the result is that this was a 40, right? Then it will create, let's say, if we're calling out this one, that's going to be like 0, 0, and if if we're calling out this one, that's going to be 40, 1, 0. And if you're going to call this out, this one out, that's going to be 1, 1. This is going to be 2, 2. Okay. Does anyone follow? Everyone follow? Simple math, right? The image temp equals image get x, y, max, dim y. This is the targeted size, and then the x is this int x, and then this is y, is this int y, and the function get means that you're going to extract that image from this array of information, and then make that as a file, basically. We're not saving the file yet, but then we're just extracting the information. It's literally getting that information from the list. Okay, so we have this temp defined. So image equal temp 0, 0. And outer is already defined here, and the naming space is already defined here, namespace. Outer is going to give it a directory, and then the namespace is going to give it a name, and then the this underscore plus x value. Whenever you don't have the quotation mark, this means this is a variable. Whenever you have something surrounded by the quotation mark, that means that this is a string, not a variable. So this is the integer x, and then this is the string underscore, and then this is a variable namespace, which it was defined right here, and then also over here as a string, and then this outer is also defined here as a string in the beginning, but then at the same time we have given a value in the setup. So we're going to use this here. What happens if you put this, like, I don't know, like here? This wouldn't work because all these things are defined over here. So even if it works, you're going to get different value or undesired value from what you wanted, because all this information is within this function. Okay. X plus underscore plus y. So I gave you this example about you have this namespace which is 40, and then you do underscore, and then this x value and y value, and then the x value and y value will be like 0, 0, or 0, 128, because our targeted size is 128, right? Because this is basically annotating the pixel location from the origin point. So if your image is here, and then this is your 0.0, this here, right here, this is defining the origin of your cutout image. Let's say 0 and then 128. That means that this is 0 and then 128 by y. This is y plus direction. This is x plus direction. So this was a 0, and then this was 128. So your origin of your cutout image is here, and then your image is going to be right here. What about 40, 128, 128? it's going to be over here, right? Because your origin point of a image is going to be right here. So this is 128, and then this is 128. Understand? Okay, someone, okay. Okay, so we now covered, actually there's one step missing. We still haven't saved the image, right? We just got an image, but then it's as you can probably imagine, this is only temporary. To save this image, you have to even before that, you have to finish your sentence with the semicolon. And also we're missing a file extension too. So we need to define the file extension as well. Otherwise, this will produce an error. So you need to give it a file extension by putting it in a string. And the quotation mark dot png. All right, so that's we now have completed the name convention. So in this convention, it's going to look like png, and then this will be some directory that you predefined. Let's say like C something something something, right? All right, and to save the image, what you have to do is and processing also have some problem with running it forever and then eat your memory like a monster. So it's a good practice to put the exit at the end, so that it doesn't ruin your computer or just keep running without without doing really anything. Okay, now okay, missing a semicolon. Where am I missing semicolon? Okay, that I'm missing a semicolon. Okay, so processing is kind enough to tell you what you did wrong. Okay, let's see, namespace, this missing semicolon. There is a no red line. Nothing looks incorrect. Cool. Yeah, everything's ready. And let's run it. Okay, it already did it. So you see, this outer folder was empty. Now I have all these images subdivided into this many images. From one image, I created 81 images, which is pretty incredible. Imagine you doing this on Photoshop one by one, image one by one. That's dreadful. But here, you can see that this is way too small for for this photo. What would be wise to do is that you would open Photoshop and put this image inside. And gauge what's the best best segmentation size. So I see this as a 1 through, let's say 1, no, maybe 1, 2, 3, 4, 5, 6, 7, 8. So I think that this needs to be 8 by 8. Let's try that. And to check how big this is, you're going to go to the canvas size, and this looks like it's 1152 by 1152. I'm going to actually resize this to 124, as I mentioned before. This is a good number to use for any sort of machine learning. So yeah, now I have, image resized, and I'm going to export this as PNG. Okay, small file. Everything looks good. Processing. Where's processing? Okay, image slice data. I'm going to just save it as 41 PNG. Okay. And now all I have to do is change this to 41, and all these images, I don't want it anymore. I'm going to delete this, and I said this. I'm going to cut it by 8 by 8, right? So 128 is good size for the this image. So I'm going to run this again. And now we have captured certain element a little bit more better than the other time, but maybe it's not quite there yet. Where was this? This looks like it's a little bit skewed, so I'm going to fix that a little bit, and instead of doing 8 by 8, I'm going to try 4 by 4, which will change this dimension to be 256 instead of 128. Let's try this again. Before running that, I want to delete this first. Okay. All right. Now it's a little better, but this is like some planning involved to cut your images. You need to know what's your center, and then you want to make sure that if your goal is to capture this circle as a perfect circle, you need to design your data set accordingly to achieve that specific effect. But then more or less, there is some relationship between one to another. For instance, like this one looks quite repetitive. Let me show you what happens if you do the factor by 2, just to show you. This will cut your images into overlap. So let's say, okay. Let's run this again. You see, like when you cut this in an overlap, it transitions a little bit better. You see a bunch of these, like a circle appears. This is very useful for machine learning purposes, because you define the circles, the edge condition in many different ways. So if you're doing StyleGAN or CycleGAN or whatever GAN that you're interested, this is a good practice to do for training your own data set. Okay.
Quick question.
Yeah.
And like I'm just wondering why we're doing the square, like because you're saying if we create like a little bit variation, it will be better. Like, is it possible to do like rectangular shaped?
Yeah, you can. Yeah, you can define that size differently over here.
Right. So is that recommended, or typically we just do square?
I mean, I set up my workshop to be the square, because it's mathematically, it's a little bit easier to deal with the even number. But you can definitely do rectangular or any other shape that you desire.
Oh, okay.
Yeah.
Thanks.
Yeah. Okay. So any other questions? Is yours running? Have you guys tested?
Yes.
Okay, great. Great. Just in case, I'm going to just share this folder with you guys. In the chat. Okay, so I think maybe this is a good time to take a break, and then we'll come back in like 15 minutes. And during that time, if anyone needs to ask me a question, I can help you with any sort of troubleshooting. But you guys can go and then come back at 10:45. Sounds good? Okay.
Well, for sure, I got some problems when installing the processing. I
Okay.
thought it was just a file, but then I found it's an application. So, but when I tried to extract the DIP files, it turned out to be.
Resume recording. Okay, let me share again. Okay, you guys are seeing my screen, right?
Yes.
Okay. So, what is TSNE? Like PCA is another very strong tool in the let me actually open actually, yeah. Oh yeah, this is good. Yeah. So PCA and then the TSNE, it just works a little bit differently. TSNE is let's say much less of a pancake than the PCA. PCA literally, like if you have a 3D object, you just squish it, and that's usually PCA. TSNE works a little bit differently. I don't know the whole process of how it works mathematically, but this method gives you more complex representation of how one data relates to another data. Let's say you have this ball of data that's in a sphere shape, and what PCA does is that you compress this and it becomes this type of information. But what the TSNE does is that it's not going to be literally 3D to 2D representation. It's more of a complex algorithm where it represents some like segmentation. This is, by the way, like don't use my quote as like scientific kind of stuff. It's just to help your understanding of how this works. It's probably completely wrong explanation mathematically, but then as just a visual kind of a explanation, this is how it kind of works. So instead of doing this flat down thing, it generates more of a like a territory like this. So that's the main difference, and you would see that in this sample. So this is the Swiss roll. Make Swiss roll is the a function that's literally making a Swiss roll, which when you click this play button, this will automatically connect to the Google's server, and then it will let you use the their CPU or GPU. So it made the Swiss roll cake, and this is the actual array of information in the correct representation manner in the Cartesian coordinate system. And now, if you're doing the PCA, you see this is using PCA. It generates literally a flat down image of what's being represented in a 3D to 2D. And then this is using a TSNE. You see, like TSNE takes more time because it requires a more complex calculation. But you see it, like this is actually a little bit of a better representation of how each color is working as an aggregation in a more of a complex geometry condition rather than a flat down pancake. You may think that this is a better representation of a data in terms of just how clear it is, but then once there is a more than, let's say, this rainbow color, and then the relationship between the rainbow colors are not this clear as a Swiss roll, it becomes a little bit of an issue because in the three-dimensional array, there might be, I don't know, like a neon yellow behind this orange dots. Then maybe the neon yellow will be so far away from here, so that this doesn't correlate. Neon yellow doesn't actually correspond to the aesthetical or data-wise similarity between the red dots to the neon yellow. But then, if you still make the pancake, neon yellow will be here. So you'll be mistaken to think that it will lead you to think mistakenly that the neon yellow is relating to the red more closely than, let's say, something that's over here as a sky blue that is more closer to the yellow. So this is visually what the TSNE is doing, and here this is basically generating a data set as a number of arrays. You just click boxes here. This is written in Python. You don't need to understand everything, but if I briefly go over what's happening here, matplot library is another library just like PZChem, and then you're importing this matplot library and then specifically calling out pyplot function within this library, and then we're just going to call this as PLT, which is more convenient than writing all these words, mouthful of a word, every time when we need to call this function out. And here importing the data sets, sklearn is this like a data set library that we call out in the beginning. So when you look at this function, this is basically our, let me bring this back here. This is basically our from here to there. It's setting up the basis for all the things that we need. You see, we're using the Skylearn data set. We're using the makes free scroll, which is this, and then we're importing tools like matplot library, and then we're importing another toolkit. This is also considered library, MLP toolkits, and then the nplot3d, which is allowing us to plot in 3-dimensional space and then make us to have a 3-dimensional representation of a data set as an image over here. And we're going to call it P3. So these are all the preconditions, which is equivalent to this one. This is a very simple code, so it doesn't require a lot of a library, but this is basically same as this process. And then the create a 3-row data set and then plot it. If you're wondering about like how this works, you can literally search this and it will tell you Skylearn dataset makes 3-row. This is a function that is predefined. And then there is a parameters embedded inside of this function. So as I demonstrated before, this is just like this, y equal x plus 1. Instead of just having one variable, here we have 1, 2, 3, 4 variables. And then we also have two returns. So instead of having one return y, this function has actually, let me do this correctly. Where is it? Okay. Yeah. So these are the variables: n, noise, random state, halt. So n sample, and no, I'm just gonna call noise n, and then the random state, and then the whole. So these are variables, and then we're expecting 2 sets of returns, and then this will spit out x and t in terms of a mathematical form. So what we're expecting from what we can do with the makes free scroll function here is when we go back here, you can define all these variables, but it seems like they only use the n sample, which is this. If you don't define it, it will just use whatever the preset value that the function has. So you see, you call out the function, and then you use the parentheses to indicate the function. I mean the variables. So you can do like, you can add another variables. It already tells you here, because this notebook is smart. N sample is one option. Noise is another option. Random state is another option. And then there are many variables that you can change, right? I don't know where the whole go, but it doesn't matter. So you can change the noise to be something else. Preset value it's telling us that the preset value is 0, but in this case, I can redefine this. Noise equal, let's say, 10. Okay. Then it will generate a little bit different graph right here. You see, now the noise is introduced so that the data set gets messy. What if I just do 1? How is it going to change? It's a little bit noisy, but still in the form of a roll cake. But if you do like 20, it's no longer a roll cake. Somebody stepped on it. Same as the other variables. You can put random state. This is none. What kind of random state does it have? it explains everything very, kindly. Random state, it's an integer, form of integer, which is a number state instance, or none. Default is none, it tells you, right? Determines a random number generation for dataset creation. Pass an integer for reproducible output across multiple function calls. So random state equal, maybe what if you do like 2, just to compare from the original roll cake. I'm going to do this. What's the difference between the 0 and 2? Maybe 2 is not big enough. 100. Well, probably it's staying in the same shape of a roll cake, but then the data distribution here a little bit differs. And then you cannot tell until each individual data set is like a very represented as a unique number. That's a little bit hard to tell. So in the case of a roll cake, it's a little bit hard, hard to tell in a graphical representation. So you now kind of get the grasp of how you use the function in the Python. It's quite similar to how we used it in the Java. I mean, these are very, very different, two very different language, but what I wanted to demonstrate is that all the computer language, you need to think very logically, and then it already has a preset value of what you can change, and then as an let's say designer, you don't have to make all this function, but then you just need to know how to use these functions to create different types of things. Like for instance, like introducing these noises, this already creates a very different shape, and then the aesthetically, this is like it still has all the aggregation, but then let's say if you do 10, now all the red and then the everything is like totally mixed up, so it's completely different. So I just wanted to show you that this impact of how variable works in play when you're working with the coding. Okay. And the figure, this is a fig is for the figure, and then the PLT is as we defined in the upper level here. It's an imported tool, matplot library. It's short for the mathematical plotting library, and we're specifically calling out the pyplot, and we are using PLT as a short aliases. So fig equal the plotting figure, which is calling out for some sort of figure to be generated, and then the AX is some sort of the return that you can expect from the axis 3D, and then this fig is right here. So this is now referenced over here, and then this X. This is another interesting aspect. Repository with example files. Angelo, what is it you're referring to? Angelo, are you here? Well, if you're not going to answer, I'm just going to keep going. This AX, let's say this is an object. Whenever you put an dot after AX something, let's say I am Sanghyun, right? And then if you call Sanghyun arm, this belongs to Sanghyun, not any arm. That's specific to Sanghyun. So that's literally what it is. There is AX already defined from here, and then you're calling its view in it. Okay, so this is embedded in the here. So this is a way to express the hierarchy in the Python, everything with the dot. So whenever you see a dot and then it's something comes here, this means that the specific part of it is, okay? So there is an AX view in it, AX scatter in it. So this is a, let's say, variables within the AX. AX has a view in it, and also it has a scatter. So these are the variables that's a subject to change, and then you are defining it right here. So it's quite similar to if you actually make this process a little bit elongated. Instead of doing this, you can do view init equals and then the AX view and not this one. But this could also work. It depends on the function, but then I just wanted to show you how this embedding process works. Okay, so this PLT show is the plot to show. Unless you specify to show, it will not show, even though it might have done the calculation for the plotting. So it's very important that you tell computer everything, every step, very specifically, task by task. You cannot expect the computer to figure out all the things by its own. We're not there yet. Hopefully we're going there, but we're not there. And this one is quite similar within the Skylearn library. Where is the Skylearn library? This is a Skylearn library. I mean, sklearn library. There is a Skylearn dataset. There is sklearn base calibration. There are so many things that's here. This is all the library that's created by this guy sklearn, and then we're just borrowing his tool to do all this calculation. So coding is actually not that complicated unless you are the designer who's making these functions. Then like you have to do like computer science PhD, and then your head will explode. But then just to use someone else as a tool, it's actually not that complicated. You just need to know basic grammar, and then you need to know how to use it. You know, like look at this. Like if you have this, you see now this as a function here, right? Because now we know that this is an imported function, and once you put the cursor here, it will actually tell you what could be done here. There is n components, copy through with and false and all this. You just need to go search for the here, Skylearn decomposition PCA, and it explains very kindly everything step by step, what each component and each variable does as a component, as a parameter to work in the function. You just need to read this through carefully and then try one thing by another, and then understand what kind of impact each the variable carries, and make sure that this is your desired the effect. Especially as a designer, you don't actually care about scientific truths. You actually want the effect. It's effect, and then the fact is a very different thing, right? So you just need to know how to use these tools. Yeah, I mean, these are all same. These are all same. So we now more or less understand how to use function in Python, right? Any questions so far? Okay, we're all good. And now we're going to this one. We were here, but then we kind of went back to it. Sorry if it was a little bit confusing. This is the similar to what we have seen in my board, presentation board. It just generates these data sets in the conglomerate. This is the beginning of the universe, and now we are using the TSNE to organize it and then make the aggregation using this TSNE function. We are not really using any of the mathematical tool that is to run the TSNE. We're just calling it out. Right, like you see this the aggregation. Let me run it again. You see, like every time it generates different results. Let me go to sklearn library. And, what was the function? Here, this is the TSNE function that we were just using. It has a number of components, which is the representation of the dimensional strings that's attached to this representation, which in our case, we use, where is the, number of component 2. Makes sense, right? It's only representing the data set in a 2-dimensional array. And the perplexity, we can change this. Default is 30 here, right? So let's define this and how these things will change. Perplexity. Maybe let's try 0. Syntax error. Did I make a typo? Maybe I made a typo. Yeah, there you go. See, this is just giant blob if you're on a perplexity of 0, and as you increase this, it will start aggregate a little bit more. This is now 10. How about like 3. Like you now start seeing some aggregation, but then it's not really compact. Depends on the your data set size and then the complexity. The best perplexity number to get the correct or desirable fit is different. Right, like this is 15. We already saw 30, so I'm going to jump to 50. Yeah, and then maybe if I bump it up to 150, maybe it will start doing weird things. It might or it might not. Depends on the complexity of your data set. It might like diverge again and then converge later. Like you see like a little bit of a spread out of this like the data set compared to, let's say, perplexity of a 30. So this is something that I was telling you about, how different perplexity could be represented in a very weird way. That's something that human brain cannot really comprehend very directly, but we just need to seek for the pattern that we like, and then we need to work around that number. Here, this is the more fun one. Here's another example that maps 1,000 YouTube thumbnail images on the 2-dimensional spaces. So this is basically using the Google Colab library, and then it's going to import the drive and zip file. Zip file is a function that let you unzip your zip files, and then under that zip file there is a specific function called zip file with the capital Z. It's a little bit confusing, but it's okay. Instead of using the YouTube thumbnail, I'm using this my dataset, the facade assembly stuff. Let's see if this works. One of the benefits for using the Google Colab is you never have to actually have all these data sets on your hard drive. You can just upload all these like data set to your Google Drive, and then you can directly reference it in your Google Colab. So it seems like this is mounted, and it mounted everything is loaded. And the image IO is another function. And this search Stack Overflow, when you click this, it move you to the this more of like Reddit kind of a space that's for the troubleshooting. That sucks. I don't think that this is a simple issue that I can resolve right now. It's not defined. Yeah, I mean, like, doesn't matter. Like, we don't have to we don't have to do this. We're going to do it tomorrow anyway. This one, let me show image collection. Okay, that's a part of it. That's part of it. That's also part of it. Well, this was to actually demonstrate the how all these image assemblies are working in working in the representation method, comparing the PCA and then the TSNE. But for some reason, the connection was made successful, but then this part doesn't work. Let me look it up real quick. Sorry about that. Okay, seems like a more complex problem than I wish to. So let's keep going. There are other things that I can cover. Yeah, so this one is not image-based, this is a text-based. So here, this is a whole novel about, you guys know the Frankenstein novel, and then this is the text file about the Frankenstein that is by chapter, and you see all these things are in text. And then depends on who's the author, they have a tendency to use certain words in specific manner in relationship to certain emotion, certain situation, to describe certain object. It's very novel specific or author specific, right? So how can the TSNE figure out what's the relationship from one word to another word? You can actually vectorize all this the text information. Let's say 1,000. 1,000 is a human language, but then this could be transformed into the computer information, which is like 010101011. That's sort of a binary format, and it's trying to find the correlation between, let's say, 1,000 celestial observations. Okay, so we just loaded the Frankenstein the text into our Google Colab space, and then to do all this the work the same as before, we're borrowing someone else's the library to do this, and then we're attaching the URL, which is the address for the this text file, and yeah, we loaded the text file, and this is explaining what it's doing, doing some basic text cleaning. If there's any emoji or there's any weird typo or anything that's not necessary for the machine learning, or something that machine doesn't understand very well, we can get rid of it altogether. Okay, so this is basically the process of how you remove all this. For instance, chapter, letter, volume, these are irrelevant to information for the trying to figure out what's the emotional relationship between the letter love and then the word hate. So these are more substantial relationships that we want to find out, not relationship between the chapter, letter, volume, right? So these are something that we definitely want to get rid of. And then there are some like spacing between the word to word. We don't want to identify that as an object, right? We want to define 1,000 as an object, celestial as an object, and then the observation as an object. And then we care about the what celestial is doing the decoration for the observation. So this kind of relationship is more important than these texture information or this like enter space. This is a process of getting rid of all this thing. And here, yeah, it basically is the same thing. We're getting close to 12, so I'm trying to, I'll try to motor through a little bit more. But this word to vec is the how you vectorize this like text information. You know, nowadays very popular like a VQGAN and or any kind of a text space GAN. What they are doing is actually instead of using the human language as a syntax, they're vectorizing those informations as a relationship from one data to another data. It's when human thinks about how text converts into the vector, and then how image transform into a vector, we might think that it's very different process, but then in fact it's actually very similar. So you know how digital color information is all in like RGB. So each pixel has a RGB information, literally like red, green, blue, and then each pixel contains the data, and then this is definitely vectorizable. When I explain how we're dividing this, the grid condition, for instance, where did my bar go? Okay. I was explaining this as a grid condition, and then this was like a 0, 0, and then this is like a 128, 0, and then this is a 0, 128. But then this 128, it can be easily replaced to 1, 0, right? This is a 0, 0, this is a 1, 0. So this is already quite binary information. It doesn't matter if it's a 2, 0. 2, 0, 2, 0 can be expressed as a, what is it? Two cases. So this, let's say this is 1. This could be 2. You just need another digit for the binary. So this, I just wanted to explain how easy it is to actually vectorize the image, and then the same goes for the text information. So alphabet has from A to Z. You just need to have a unique the binary sets of a number to express A to Z, and then you just need to array it in very, very long binary form to express, let's say, like array. A as a something, R as a something, R as something, A as something, Y as a something, as a binary information. Right? So this is what the word to vec is doing. And this is running PCA and then the TSNE at the same time. This is the word to vector. The WV is short for the word to vector here, and then index to word. It's just like procedural things that's keep adding stuff or keep referencing stuff that's embedded in the function. And once we plot this, we can now see how one information relates to another information. A very interesting thing here, you will find many interesting things within this grid, but the pleasure is somehow very related to the gave, became, air, and what would be a good thing? Old, young, woman, girl. When you're describing the, let's say, a woman's or girls, especially young females description, body, old, young, they're all very appearance based, right? So this is quite interesting to see, and what gentle and voice. I can imagine the author really favored gentle voice to be used as a kind of narrative voice in his novel, and loved, affection, they're very similar, but then there is a word never. So in the novel, there's the Frankenstein is a never loved monster. So this makes very much a sense in this form of a novel. Beloved Elizabeth. Elizabeth, on the other hand, was very much of a loved character instead of a never loved. So these are the these are really telling very interesting information about how TSNE is really good at actually finding relationship from one vectorized information to another vectorized information. So this is going to be it for today's the lecture, let's say, or workshop. I will stay from now to 12:30 to troubleshoot anyone's problem. So you're welcome to stay as long as you can, as long as you want. If you don't have any question, you can leave. But make sure you practice this, what we covered today. After today, I mean tomorrow. And if you can, just bring some images. It's okay if it's like just a random set of images. You working with your own image sets just encourage you and motivate you more to really personalize the process of this workshop. Okay, so I think it would be great if you guys can bring your own data set. But otherwise, you're free to go. And if you have any question, you still can remain here and ask me questions. Okay. Yeah, thank you, Alejandro. Any questions?
Question. Oh, sorry.
Yeah.
Did I go first?
Whoever want to go first, go first. John, you want to go first?
Okay. About the processing script.
Yeah.
I managed to run it, but like half of the image they are just looping, is repeating images. What
Can I see?
did I do
Can you
wrong?
share your screen?
Yeah, sure. Hold on. Let me organize it a little bit. Share screen. Yes. Yeah. So is it about the original image?
Can you open the original image just to see?
Yeah, of course. Yeah. This is the origin. Wait, sorry, I'm bad. open with photos. Okay, yeah. I will put it on this side. Yeah, so for the last few images, they're just looping itself.
Hmm.
Mm.
Can you change the factor to 1 in your script?
Hold on.
Factors.
Factor. Okay, let's find it to 1.
Mhm. Did you check how big is your image? Can you
My
open your?
image is
Yeah. Okay,
good. Yeah,
that should be fine. Yeah.
yeah. So let's try. Save, run, and go back. Output. A little bit. A little. No, nope. The same.
Huh.
No, wait. A little better. A little better. Yeah.
Yeah, I think this is correct actually.
Okay.
You see the coordinate here, right? These are
Yeah.
coordinates of your images, and then
Yeah.
it has all the images that you have put in. I think it's just a delusion that the one image look too similar to another because it's actually quite repetitive image to begin with, right?
Okay. I'll pick a better one then.
But you know, having this repetition, it could be interesting. You saw my the TSNE assembly. It has a many repeated kind of facade elements with very small variation. It would be interesting how this will be this set will assemble, or and this like, in the similar aesthetic will assemble as a whole set if you're yeah, if you're using the when you're using TSNE tomorrow. So if you
Okay.
want to just like you know collect bunch of circuit boards, I think that would be interesting.
Yes. All right.
Yeah, just download bunch of circuitry images. Let's do that. Yeah, I think that's interesting.
Okay.
Yeah, and if you want, you can even put these images into Photoshop and then make all the color scheme the same. And then if you just purely want to focus on the geometrical condition of a circuitry, you can do that too. But if that's too much work, it's totally fine if you just want to do it as is.
Okay. Sure. Sure.
Yeah, yeah, yeah.
All right. Thank you.
Yeah.
I'll stop sharing then.
Okay. Anyone else?
I wanted to ask something from your project that is on the videos,
Okay.
like from your thesis.
Yeah.
So how did you correlated the program in your of the building with the facades? Was that like a manual process, or was machine learning involved in that?
So let me open my video. It's a little bit of a both, you know. I mean, I hope that everything can be through machine learning, but then the oftentimes what I personally have encountered as a problem is that it requires a lot of a data set, and then it requires a lot of a training. So sometimes actually doing it manually is faster than doing it through the machine learning. Sadly, with the as an individual, it will be a different case if you are not an individual. If you're an organization, that's a different story, right? But then as an individual, there is a limit to it. So you were talking about this project or the one that was listed on the workshop.
Yeah, the one that was listed on
Workshop.
the work.
On the workshop, that's that was mostly facade study, but then it has an element of a element of a simulation. Just now here in the condition of a space, there is a just in general just a public and then private space, and then the space of the public and then the private was determined by the how deep you are in your in this like a building. So this is a plan, and then if you're deep inside of the building, let's say like here, that's like a private condition, and then if you're on the outside, you're the public. And then I use the 5G network, how they propagate as the wave between the cities to determine what or to speculate on what's the future if you're, let's say, designing a building based on your connection to the outside of the world. And I did this 5G simulation in using the Grasshopper, testing different types of condition. This is when your building is enclosed. This is when you have a courtyard. This is when you have a courtyard with the open end. And this is with the circular courtyard, and then like so on. And then it creates like a different types of connection condition under the 5G. And then this is the simulation result on the plans based on what I had harvested from the TSNE. And this creates this like a map of a dark spot of the 5G. So in this like a dark spot, that's usually the private space, and then on the exposed spot, that's the public. So in the public space, you are living wireless life, and then in the private space, you live a wired life. This is kind of a theme that's going on in my work, which is thinking about speculating on a future where human agents are moving or living with all the other objects in the world. For instance, like a 5G connection, machine agent, or any other agents that's relating back to the contemporary urban society or the near future contemporary urban society. So this was the part of my kind of a program forming factor in the project. So you will see there are these like a filleted condition that is to mitigate the 5G connectivity. There is a research paper that's published by the NYU Sound Lab that when you have the soft corner, it cancels out those like the wave propagation a little bit more. So you're living in a very much of an insulated environment from these wireless propagation wave. Yeah. So to answer your question, this is the my answer. But yeah, I don't know if that
Thank
was.
you.
Yeah. Okay.
Very interesting. Thank you.
Yeah. What else? I know, Ife, you were trying to ask me a question for long time. So yeah, what's
just wondering how many data, like the image we need to prepare?
Many is better, but then minimum 30, because we're going to use this like image splice tool to subdivide the images. So let's say you bring 2048 pixel by 2040 pixel images, and then divide that by 128. Then that will result in 16 by 16 grid condition, right? Then it will create how many images? 196 images per one image. So if you bring 30, that's going to be over 3,000 images already, right? So ideally, that's the situation. But you don't have to have that many. let me show you interesting results from.
Are those images has to be like the same size, like 1280 by 1280?
It can be 256 by 256, but then we're now in the era that we can do so many cool things, but then we're limited by the computational power. So if your image size is bigger, it means that it requires more memory, so that you are not going to be able to run it in some cases. So that's why I'm trying to limit the size of your images, and it's the final result, final images that we're going to use for the assembly to 128.
Okay.
Yeah. There is a very interesting photo or experiment that I did that I want to show you guys. Where is it? TSN. Maybe it's on the. I'll find it for tomorrow. I have this like a cat photos. So it's segmented into like multiple parts. So basically, if this is cat, when you segment it, you have this like a ear, and then the ear, and then like the eye, nose, and then like. But then if you do it for the multiple cats, you will have all the eyes segmented in one area. You will have like a paws on one segmented area. It will have like all the tails in one segmented area. It makes this like weird beast that has like 1,000 eyes and 1,000 paws. So it's pretty interesting. So it really shows the power of the TSNE, how it is good at segmenting or the categorizing different parts of certain things, and then just making it as a whole set. Originally, this tool, especially the code that I'm using, was originally developed for the linguistic purposes. So like this one, symbols. Yeah, like you look at this, when you look at these like ancient the characters, you at least want to know what belongs where, right? Some are like Egyptian language, some are more like from other areas, some are Greek, some are like maybe you can do like Chinese characters. It doesn't matter, but then it's really good at making the correlation between the one to another. For instance, if this looks very similar to, let's say, this one, even though it is in a different font, it will try to find a similarity between one to another. So it's not only good at making a good family of things, but then let's say you don't know what this exactly means in this types of a font, then it will try to find a correlation with the something else that's in a completely different family. And it will suggest that's similar to that another. And then this similar tendency can be found in the this text information. Like you would never, let's say, relate. I mean, various means that make sense, but then some words doesn't make sense for the human. But then often, in many cases, you will find a lot of things that doesn't make sense as a correlation from one thing to another thing. But then TSNE finds it, and when you like think hard about it, oh yeah, maybe that makes sense. So it's really good at finding a pattern that human usually cannot come up with. When you look at the like this one, like, you cannot exactly tell, especially in this area, what's the main driver for the TSNE to think that this relates to that thing or that relates to this thing. But then, like at the end, like in a larger picture, kind of make sense. So think about what TSNE does, and then just prepare the whatever you're interested in. Don't think too seriously. Just this is workshop. You're just having fun for free. So yeah, like it could be your friend's face. You could literally go to your, I don't know, high school yearbook, and then take all the photos of your friend's face from your high school, and then try to find the similarity between one friend to another. That's completely doable. If you want to be a little bit more serious about it, you can collect your favorite architects, like maybe 3-4 favorite architects projects, and then trying to make new architecture, like the assembly out of these four of your favorite architects, right? And then if you have that sort of like a more dense information, like architecture, then you would have a better chance of tessellating that more in detail. You saw my presentation today, and then earlier on I showed you how I'm going to use the not this one, three-dimensional like a tessellation tool using like Houdini and then the Blender to create this kind of articulation. But you know, you don't have to use architecture. You can use cat space. You can use whatever the image that you want to use. That doesn't necessarily need to be architecture. Yeah.
Oh, that's very interesting. Like for the calligraphy you just showed, like what I'm just wondering what's the end result of that? Like those ancient, yeah, those ones.
I
Like,
can run this today and then show you the result tomorrow.
oh, thank you.
Yeah.
Because they remind me of one like artist called Xu Bing from China. Like he had like a book called A Book from the Sky. He created a bunch of like characters based on the existing Chinese characters, but it's completely alien. He just made them up.
Ah, okay. Yeah, that's cool. Yeah, so endless possibilities. Okay, so let's have fun. Please have your data set. Like, I really want to see all these variations. This is definitely my version, and I want to see as many versions as I can. That's my goal. Tessellation part is like very like technical, like, and then like once I cover it, like you don't have to think twice about it. Just need to play with the tool. But then this TSNE part, how you see like one relates to another thing, and then how you use that as a design tool. I think that's really the strength of this workshop. And then there's something that you should definitely learn. Houdini script, I can write it and they give it to you, but then learning how to play with this and then how to think computationally is very important. And my goal for the workshop is to give you guys that sense of a I don't know, sense of a workflow or sense of a logic. So that's why even though like this is super boring stuff, I'm like explaining a step by step to really give you an idea how actually it is not that scary, and then you can use whatever the tool that's available out there and then use it creatively rather than scientifically. I think that's pretty liberating and pretty strong tool. Okay. Anyone is that all, Yipe?
Yeah, thank you for your time today.
Yeah, no problem. Any other questions?
I have a very small question about, because I was not able to catch the step of add picture in the coding.
Yeah.
Very
Let's
small
do that.
question. Yeah. So do I need to screen share or yeah? Just
Yeah, you should screen share.
okay. So yeah, I just compared the two coding, so I'm sure the only problem now is just to get the picture in there.
Okay, so
Yeah.
you don't know how to put the
Yeah, I don't know.
address. Okay, so go to your Finder. Finder.
Okay.
You know your
Yeah,
yeah.
so I just need to directly find the file for my material collection.
Yeah. So if you let's say this is your file. I mean this isn't your file, but then let's say this is your file. And then once you click right click there, like let's say this is your image.
I think it is. Oh, yeah.
And then you can
That's
look at
my
the property. No, right click that screenshot image or whatever image that you want to use.
Oh yeah. I'm looking for wait. Hey, sorry. Oh no. Anyway, I just add a picture.
Mm.
Okay. So like
Yeah.
this one. Yeah.
So if you like that, just right click that.
Oh, right click.
Yeah, right click. And then you can go to get info. Then it will tell you the directory, can you do more info? Click on the more info, expand the more info. Okay, that's not it. I have a Mac. Wait a second, I can open it.
Oh, so it's a different way in the Mac. Okay.
Yeah. Let me actually search it up right now.
Is there any shortcuts for adding a picture in it?
Okay, here on your Mac, click the Finder icon in the dock to open the Finder window, and then choose View, Show Path bar. So here to just go back to your go back to your Finder, and then the choose View. I think if you expand this one, or here, actually this one, click that one.
This one.
Yeah. List, yeah. Go through the list. It will be really helpful if I find my laptop and then open it. Let me share my screen for a second.
Okay.
So this has 10 ways to get a file path on the Mac. Let's see how this guy does. Okay, file, get info.
Yeah.
Oh yeah, you see here, where Macintosh.
Oh, okay, I see. Just copy paste the file path.
Yeah, but then you should replace all this. You see here, instead of using the slash, like my code, this one uses like a mark. So replace all of this to this one, then it should be fine.
Will it remember the like half of the file path, and then when I want to add some new photo in this file, and when like I type in some like the file name, and the US will automatically like jump out like in Visual Studio Code?
No, you just need to, if you want to use, let's say, this image, you just need to find the directory of this
Okay, so just manually plug in the
Yeah.
path. Okay, I see.
Yeah. So if you
Thank you so
let
much.
me show you my code just one more time. So what you're doing here is actually, what you're trying to get here is the outer, right?
Yeah.
But when you look at my zip file, where is my image? Okay. When you unzip your unzip the folder that I gave you, or the zip file that I gave you, you have the data out there and image splice PDE, right?
Okay.
You need to put your image in the image that you want to cut in the data.
Okay.
And
I see.
and then the outer is actually the after you cut the image.
Yeah. I mean, for some images I've collected, I've already cut them into some very small sizes, because I saw the sample you showed us is like it is in like very low resolution. It seems that yeah.
Yeah, that data set is already cut into small pieces. Yeah. So if you already cut it, you don't need to do this process.
Okay, I just cut a part of them, not all of them.
Okay, okay.
Yeah, I was wondering if it's already been very small. Does it bother for it to be divided further?
No.
Okay.
Yeah.
I see. Okay, thank you.
Yeah. Great. Okay. Anyone else? I feel like everyone's falling asleep. So everyone good? Last call. Well, if that's the case, I'm going to see you guys tomorrow at the same time. Tomorrow is going to be a little bit intense in terms of how much the Python coding that we're gonna do, but it's going to be okay. And all the fun part is going to happen on Wednesday. All the Houdini, Blender stuff, like it's all on Wednesday. So if you don't want hardcore Python, it's okay. Yeah, but you can, I can still give you guys like the code or the TSNE script tomorrow. But if you are willing to learn the Python, just if you don't have any experience prior to the this workshop about the Python, just search the Python syntax. Just watch like one YouTube video that it gives you for the most introductory part. You can watch like for 15 minutes. That's 4 hours. I don't want you guys watch 4 hour. That's way too genetic. Okay, this should be good. Yeah, this is the only 5 minutes, but then it will give you some idea about how Python syntax works. So just getting to know about what's the basic grammar about the Python would be very helpful. So I'm going to just put this in the chat right now for those of you who wants to learn a little bit more basic and then get prepared for tomorrow. Yeah, this is it. Now, of course, you can always ask me questions if you don't understand any parts of things that I'm going to cover tomorrow. It's just going to be a little bit intense in terms of not just only in terms of the Python, but then mathematically. Okay. That's it. And thank you everyone to stay very late for the workshop. Very excited for tomorrow and Wednesday. I hope that you guys learned a lot from today. This was just to warm up. Tomorrow is going to be intense, and Wednesday is going to be very fun. Okay, I promise.
Okay, thank you. Bye.
Yeah.
Good night.
Yeah, thank you. Bye.
Thank you.
Thank you, Sanghyun. Bye bye. Have a good night.